Welcome to all. My name is Dr. Mansoor Nilikal, and I'm an enterprise fellow at Physical Sciences Data Infrastructure, PSDI, and I'll be chairing today's session. If you're new to PSDI, PSDI is a UK-wide initiative building a digital platform to make physical sciences research data more accessible, reproducible, and easier to share. In today's session is a bit different from our usual webinar format, as this is a launching of a new webinar series called From Project to Platform, New Resources on PSDI. So this series is all about demonstrating tools and resources developed through the PSDI's first funding call in 2025. These were like short 6 months projects funded through PSDI. The main goal was to introduce them to wider audiences and to connect them with potential users. So today's theme is AI-driven material discovery tools, and we have two talks. One is Universal Hyperactive Learning for Machine Learning Interatomic Potentials by Professor James Kermode. Then we also have MOFevaluator, a cloud-based platform for process-informed discovery of MOFs for carbon capture and beyond by Dr. Peter McCallum and Professor Susana Garcia. Let me introduce our first speaker. James Kermode is a professor in School of Engineering at the University of Warwick, where he directs the EPSRC Center for Doctoral Training in Modeling of Heterogeneous Systems and the Warwick Center for Predictive Modeling, both of which have strong synergies with PSDI activities across the full spectrum from theory and algorithm development through research, software, engineering, and applications. Today, he will be presenting, as I mentioned, the Universal Hyperactive Learning for Machine Learning Interatomic Potential. James, over to you.
Thank you very much for the invitation to speak here and for the introduction. So I'm going to be telling you about the project that we've done over the last 6 months. It was a project that was carried out mostly by postdoc Tom Rock. I think Tom is actually here on the call today, so he'll be able to help with answering questions at the end if necessary. And to start with, I'd like to thank and acknowledge PSDI funding for carrying out this work. It wouldn't have been possible without, so it's nice to be able to share what has come out of this back with this community today. So let me unpack a bit what the title means. Those of you who've been using machine learning interatomic potentials over the last few years will understand how they've really revolutionized many areas of atomistic simulation. In particular, in the last few years, we've seen the emergence of so-called foundation models. So these are very transferable machine learning potentials which have been fit to very extensive databases. The picture I'm showing here is one of the first of these, the MP0 MACE-based foundation model, but there have been many others, both around the same time and since, with similar aims, which is to encapsulate a vast quantity of density functional theory data from databases like the Materials Project and others in a message passing equivariant neural network, which can then be used to make predictions across vast areas of chemical space. So you see lots of different applications here, and it's kind of amazing that the potential is even stable for all of these different application areas, let alone reasonably qualitatively accurate, and can be made quantitatively accurate in many cases. I had a very small involvement in this particular project. I worked on dislocation application here, so just one of these little applications, but there were many others as well, to systems ranging from water, amorphous materials, nanoparticles, zeolites, etc. So this is clearly a huge data challenge, and therefore within the remit of PSDI. But the specific goal that we set ourselves in this project was focusing on fine-tuning these models. So once you have a model which is general and is able to run dynamics and to do simulations, that's a good start, but often it's not sufficiently quantitatively accurate to calculate the quantities of interest that you care about for your specific simulation or application. And in order to improve it, you typically need to add more reference data that's finely targeted at the specific calculations that you want to do. So what we were looking at here is ways to find, subselect that data automatically and to do it in an efficient way. So let me first of all tell you what we've built, what we've made available through this project. We've made a Python package called ase-uhal. ASE stands for the Atomic Simulation Environment, so that's a widely used Python framework for doing molecular and materials simulations at the atomic scale. And ase-uhal is a plugin or an add-on to that. It can be installed from PyPI with pip install ase-uhal, and there are different variants The one that's probably of most general interest at this stage is the one that uses MACE as a backend. It uses the MACE graph neural network potential to drive things. So that's all out there and released together with documentation and tutorials, which are available on GitHub pages. We also ran a workshop, just over a month ago, actually, here at Warwick, just towards the end of the project. Tom did a fantastic job setting that up, inviting a number of other people to speak on related topics of mixing together interatomic potentials at different scales, different approaches to fine-tuning, such as freezing earlier layers in neural networks, and also incorporating constraints to give desirable physical properties and machine learning potentials. So related topics being developed by others that are synergistic with what we were doing here. And then finally, Tom has put together a benchmark application to show that the new functionality that has been developed and released in this Python package is actually useful, and that's on indium gallium phosphide alloy. So a reasonably complicated ternary semiconductor, III-V semiconductor. And I'll say a little bit more about that at the very end of the presentation. But the headline is, by adding just 50 carefully selected configurations, we do a better job than selecting at random, and we make some quantitative improvements in target properties. And yeah, this is all available on the PSDI resource catalog. So in a little bit more detail, what does the ase-uhal tool that we've developed do? It uses Bayesian approaches to select good choices of data sets to improve models. And this is important, as I said earlier on, because if you start with a foundation model, it's already great that it gives you stable dynamics. That's a good way of generating candidate configurations. So that's an easy way of getting lots of unlabeled structures that you could, in principle, use to update models. But we have to decide which ones to label. Which one, and that's the expensive step. Generating the configurations is now relatively cheap, but if we want to make better models, we need to label some of them, which requires doing expensive electronic structure density functional theory calculations on them. And the naive approach would be to do that completely at random. What we are aiming to do here is to pick instead the most informative configurations, so the ones that are most different to one another and the ones that add the most over what we have already incorporated in our foundation model. Of course, this isn't the first such approach. There are lots of other ways of doing active learning, and our particular approach builds on something that was done earlier by Cas van Doord and co-workers in Keppel Chinese group in Cambridge, and also Christoph Ortner and Matthias Sachs at UBC and now Lancaster. And the idea of hyperactive learning is to drive a dynamical system kind of adversarially towards regions of high uncertainty. So you have some kind of uncertainty estimate for your model, and you use that uncertainty estimate to bias configurations towards high uncertainty regions. What we add on top of the previous HAL approach is essentially lifting the restriction of how it was originally conceived, where it would identify one new configuration, run the expensive DFT labeling on that and refit. And we've also generalized it so it works with different machine learning potential architectures. So the way that the code has been structured, you can plug in different choices of the base model and different ways of doing the selection. The basic idea, as I said, is to start by training a committee of models rather than just one model. And where we have quite a bit of training data, so this is a toy 1D example, but it gives you the basic idea. In this region of parameter space, we've got quite a bit of data. All of our committee members are similar to one another, whereas over here, there's big variation. And so the standard deviation across the committee is large, and it's indicating that we are likely to need more training data in that region. And what we do essentially is bias the dynamics by taking a mean model and pushing it towards regions of high uncertainty. So we start with the true potential, and we use our model prediction, which is not quite right. It's actually pretty good in this region. It's not very accurate over here, but our uncertainty estimate is large in that region. So when we do this mean model minus some scaling factor, which we have to choose in order to get a good balance, we make it more favorable to explore regions like this, essentially. And then we pick out a configuration that has large uncertainty. We could do one, we could do two at a time, we could do multiple. We add them to our training set and repeat. As I said, the key change between ase-uhal and the original HAL approach is that in the original HAL approach, The schematic is something like this. You run biased MD, pick out the most informative structure, label it with DFT, and then do an update, and keep going until model is seen to be sufficiently accurate. What we've done is essentially batch the selections so that you can run dynamics, select a whole bunch of structures, taking advantage of a nice feature of the way that the Bayesian inference works, that you don't actually need the labels in order to compute the posterior variance, to compute the uncertainty, but those depend only on the configurations. So we can actually identify lots of candidate structures, run them all together, and then refit the model, and hopefully get faster time to science by getting higher throughput overall. This is the demonstration application showing that this is working fairly well. So this is the ternary indium gallium phosphide system, starting from a good foundation model, the MACE MPA model, which is generally good, but not giving a perfect description of this particular material. And then using the bias dynamics to pick out just 50 configurations, which are evaluated with DFT, added to the training set and used to perform fine tuning. And to do a fair comparison, we did the same thing with random samples from an unbiased version of equivalent dynamics. So it's hard to do it completely equivalently, but we did the best job that we could. And we see an improvement in both the lattice constant. So the biased model is the orange one. It's getting significantly closer to the reference results than the one based on random samples. Of course, the improvement over the foundation model isn't perfect here. This is a small test, and we would need to add more configurations and probably iterate a bit more. But as a proof of principle, we're very happy that this came out within the short lifetime of the project, which was mostly focused on implementation, dissemination, code documentation, etc., rather than the scientific application. So it's great that we managed to get a bit of a proof of principle in, and we'll wrap that up and do more on it now that the project has formally finished. So as I said, this is already out and available. We ran this workshop last month. Actually, it came in very handy at an industry study group, industry challenge that we ran more recently, earlier this month, where it was great to have this method available so that within the tight confines of a 3-day event, we were able to fine-tune a new machine learning potential for a real target application. It was iron, chrome, nickel as used as a candidate for nuclear fuel cladding, and we could really get a model that was significantly improved over existing foundation models in a very tight time frame with very few DFT configurations. It was presented by Tom earlier on to the PSDI community, and it's already going into use in a variety of PhD projects here at Warwick. So we're happy with the impact at an early stage in this project. So to wrap up from me, this package is out and available. It works across different machine learning potentials, ACE and MACE out of the box, but it's designed in an extensible way so that others can be added. The batched workflow means that DFT isn't in the inner loop anymore, and so you can run lots of calculations together. And we already saw some improvements over naive random sampling approaches on this highlight application. It's available now. So here are the ways to download, to find the code on GitHub or the documentation, or from the PSDI resource catalog. I'll pause there. I think we're not going to do questions now. We're going to go straight on to the second talk. So I will stop sharing my screen and we'll come back, and I'll be very happy to answer questions later on.
So this is PSDI's platform, resource themes. These are all the resources that are currently available. These are all the latest resources. James's ase-uhal, you can find it here. So this is how you access it, and please do take a look. Our next speakers are Dr. Peter McCallum and Professor Susana Garcia from Heriot-Watt University. Peter is a research software engineer who develops web-based research platforms with a focus on making them practical and useful beyond academia. Susana is a professor in chemical and process engineering and an expert in low carbon technologies, including carbon capture and AI-driven material discovery. Together, they will be presenting today a MOFevaluator, a cloud-based platform for process informed discovery of MOF for carbon capture and beyond. Peter and Susana, over to you.
Thanks very much, Mansoor. Let me then get started by just providing a little bit of the background and the vision for this project. So we are very grateful to PSDI for funding the the MOFevaluator project for the past 6 months. This project is really rooted on a lot of work that we have been doing over the past years on mainly this research question, right? We are here in the team at Heriot-Watt University. We are experts on developing low carbon technologies, specifically carbon capture ones. And the question in this space for many years has always been, what is the optimal carbon capture technology, and in turn the optimal material for a specific separation and a specific case study, right? Ultimately, we want to decarbonize our energy systems. That means that we'll have to capture our CO2, our carbon from many different sources, and equally there are many options for which you can send that CO2 to, or in other words, there are many CO2 sinks. So for each of those potential combinations of CO2 source and sink, the question was, what is the optimal process? What is the optimal material? So then we focused on metal-organic frameworks as the materials to investigate for this specific process. And the reason for that was very simple, because these metal-organic frameworks, or MOFs, for those of you that are not familiar with them, are very interesting and fantastic materials from the point of view of the chemistry, in the sense that they are the 2D or 3D porous crystalline structures where you can actually change the metal, or you can change the linker that connects all those metals in the structure, but you also can change the pore topology. What this means is that, in principle, if you combine and change all these different parameters, you have databases of potentially millions of possible materials. In other words, your chemical design space is really broad, so it provides you a fantastic playfield to kind of understand what you can do in the materials space for a given carbon capture application. So obviously the question then here is like, what is the optimal MOF for one of those specific case studies that we are interested in looking at? And ideally, our vision here was to kind of develop a tool that, you've got your materials in your database, in this case MOFs, right? You've got different applications. Here we have exemplified that with 3 different types of applications. And you have a tool to screen those materials for all those applications. You can very quickly identify what they might be interesting for, and then you can then follow up on that specific one. So that kind of accelerates development, accelerates progress. And then you move into the lab when you really have materials that really show promise. So then this is what we envisioned like 6 years ago. So we thought about, can we develop this tool that connects all the different elements that are important in the materials discovery process, and then provide that tool to the community. So we developed what we call our Prisma platform, and the idea here was to connect all the way from the materials space to the life cycle assessment, going through the process and the techno-economic analysis. So in short, we aimed to drive the materials discovery process by understanding the system first, so following a systems-based approach and understanding what is important on a scale, and then how that translates into different key performance indicators that we can make use of for this materials discovery part at the very fundamental level. This was obviously a joint effort. It wasn't only Heriot-Watt University, it was a series of partners in Europe, in the States, that were working on this for a few years, and the result of that was the Prisma platform that was published. It's going to be a couple of years now, and it's, open access article if you want to know the details. So results from this type of analysis that you can get are things like the ones shown on this slide. So basically in here, we screened materials for a specific case study, and we compare them against the benchmark technology, in this case, an MEA-based process for carbon capture. And what you see here is the net carbon avoidance cost, which is our ultimate metric to drive that materials discovery. So the cost in euros per ton that the carbon capture process imposes in your system versus a couple of different KPIs from the process layer. Each dot is a material, is a MOF in our database, and then you can see very quickly whether they show any promise when it comes to outperforming what is already out there. And again, on the right hand side here, you can very quickly assess for different point source carbon capture systems. So depending on where you capture your CO2 from, natural gas, combined power plant, coal-fired power plant, or cement plant, how these materials compete with these dotted lines, which is the benchmark. So, a lot of very interesting insights that you can get very quickly. So what happens then is that we develop this platform, we develop all the data flow, and this is a summary of how the data flows into this Prisma platform, which was coded in Python. And the main message here is like we collected a lot of data. We gathered all our databases that we needed in order to perform this study, and we started running case studies and getting KPIs. We get over 50 KPIs for each of the case studies. So we started really getting more and more data, and it started becoming a bit unworkable in the sense that ultimately, the aim here is to share this with the community so they can make use of the tool. So how can we then refactor all of this in a way that makes it easier for anybody that wants to interface with this tool? And this is where the MOFevaluator project came in. So our aim then was to, again, the ultimate aim is to accelerate research on this type of technologies and just assess whether a given material or a group of materials are promising for a given carbon capture application. But we specifically focus in the MOFevaluator on two objectives. The first one was to develop a database, so moved into the database domain with all the properties of the MOFs and their KPIs for the different capture process that we investigated. And then the second objective was to develop a full stack web application for the MOFevaluator that enables that interface and that interaction with any groups that are out there and are interested in making use of the tool. So Peter was the research software engineer that did all this nice work. So I'll pass it over to him so he can give the details.
Okay, thanks. Okay, so to give a good idea of what we've been working on, I'll just go straight into a demo. It's worth mentioning we have this large legacy code base, which is very structured and very large. What's been built in the last 6 to 9 months is a new system that works alongside that existing system. So we have our simulation engine, which is what's described by Susana, that runs on a laptop in several cases and different researchers and different groups we partner with in Switzerland and so on. That kind of system operates on a single machine, but what we've been working towards is having a system where data can live dynamically on the web. So we built a full stack web system that houses a database, a visual front end, so we can explore data in different ways. We can do that privately. We can also share those visuals as we develop the systems further. And we also have an API service, which means laptops and other machines, high performance computing, that can interact directly with our database through an authentication system. So I will bring in demonstration. This is our visual sort of front end, and the first part of this, the entry point for people to visit the landing page is a series of projects. So this represents similar content to which will be shown on PSDI once we go through the final screening process with Aileen at PSDI. Obviously, the MOFevaluator project is the one that's relevant here, and we have descriptions. This will be a public web page in around a week or two. We're finalising a date just to have all the content verified. This will be public and available and mirrors a lot of the information that will be on the PSDI system. So we're delivering data set through PSDI, linking with cross-data search. We have a Python application for interacting with our API. And we have 2 live web services. One is the visual part you're looking at now, and the other is a more hidden part, which is what works directly with Python for any use case. So there's various content explored within these. Also, the main item that we're building on is our database in the background. So this serves as a way of interacting with the database for us to browse for our own benefit, to explore materials. This is a list of materials that are currently in the database, MOFs. We can search for patterns in text, so we can find MOFs that we're looking for. We can explore each MOF by clicking on it. Within here, we have isotherm plots for carbon dioxide and for nitrogen. And the line shown is a reference line from a simulation. In other cases, we also have some experimental data. We're able to do things like to explore different temperature set points based on the reference using calculations, and start to explore what the underlying properties of this material so that we can explore how we might use it in an application. We also have 3D visuals where we can explore the crystal structures. and we have information that we can browse. So again, some of this is similar to what will be shown on PSDI. It's probably a little bit more in terms of the visuals, but we have a link to be made. We're almost there with that, with the PSDI team, to link with the cross-data search. So this information will also be available through PSDI and will link to this resource. So within this materials browser, we can also add in search terms. So we can start to narrow down our search based on parameters that we're interested in. So we might want to narrow a window down on certain properties. And add other, we can exclusively look for experimental data as well, and close these filters. So we're starting to try and make our databases far more dynamic. In the past, our data was stored in a more traditional way in CSVs, and these kind of interactions would have taken quite a bit of time to develop Python notebook in each case to try and explore, and everybody would have a different way of doing that. This is interacting directly with the database, and it's pulling the information live. It's obviously very fast, pulling in thousands of records, and we can really start to leverage a lot more insight into the data because of the database that's in the background. So our simulations are based around case studies where we study sinks and sources, different processes. So we have a case study viewer where we can look at situations where we're interested in certain sources of carbon. This is direct air capture in this case. And we have various studies relating to carbon storage in reservoirs and mineralization techniques and so on. So there's a wide range of case studies being studied. Again, this interface is a way of exploring that information in a rich context. So we have results which are encapsulated in a .NET-CDF format. We can click and download those. We have a way of browsing more detailed information on our case study. This one's in the UK. We can look at headline results. These are MOFs that are performing in certain, that have passed certain feasibility checks. These are the top performing MOFs, and we have different ways of visualizing the performance, really to allow researchers to come and explore their case studies in a very quick and reliable manner, not always going to code and notebooks to do this. So there is a pipeline in the background also to upload data, the various checks that are done. So this is a part of the background process, as well as having a database schema where there's around 50 different data tables. We have various ways of checking the data that's coming in. We look for things like associations between different files. There's a quite complex data pipeline in the background, but that isn't something that the general user worries about. We maintain this in the background. And we have a few future developments that we're working on. One is to build on a notebook type format, so where we can build lab books, we call them. We can come and add content, we can add markdown content, we can add plots. So we can add various different information here. This is a work in progress, and it links directly again to our data set and allows us to leverage the information quickly. The final thing I'll mention is a very early prototype for a chat agent. There is a follow-on project, which Susana might say a couple of words on, it is heavy AI focus in materials discovery, and this area is where we're planning to take the portal at the next stage. So this works in the usual kind of way. You ask questions. It's very limited in the background just now, so this is early days, but that's the direction and future work that we're going towards with the platform. I have a quick note back to the slides just on the architecture, because there's quite a lot going on. So just to close out without going into too much detail, we have our existing Python environment that people tend to work on. We had a quite traditional sort of data structure around CSVs and YAMLs. Our different iteration through this was to move towards a relational database and introduce our package that we've also delivered as part of the MOFevaluator. So this is an easy-to-use pip install package, which allows direct access to the data. We have gone away from having isolated systems on computers that are pulled through GitHub to having simulation engine which you can run on different computers, but it's linking to data that's on our web server. We've got quite a complex system of authentication. We have legacy data, so ingest, and we have our visual front end. So this is what's happening in the background. And the flow of data, really, when somebody makes a simulation, it goes straight into our database and it's available to view by colleagues as well as the researcher themselves. And the next steps for this is to make more of the site public. And we're starting to do that in the coming weeks. And going forward, this is our big platform to build on for our current big project and future work. The last note is that there's a lot going in the background, but what this boils down to for the user is Python sessions that they're already comfortable with and nice user interfaces that we can manage this complex system in the background, all relying on this single database, a single truth of data. Thank you.
Do you want to show a live demo for the audience, uploading the data?
I can in code, which is ultimately how you do it. The first thing to mention is for the project, for MOFevaluator, our work focused on delivering the visual system and the way of taking data from the system also. So the data set that's linked to cross-data search, or will be very soon, and that's a major deliverable. So that's data that we're offering out and making it highly accessible. So the putting data on is, there's a lot sort of going on. Oh, I'll bring up this one. So principally, it's us, the internal group, not just the MOFevaluator team, but our key collaborators on a following project. So we're putting data into the system for now, and that's the current setup in the foreseeable, but we're hoping that we can find a way of, well, we have mechanisms to it. It's more a sort of institutional thing, having data uploaded. So we start to discuss that sort of further. But
so basically what we are doing is like we are testing all of this, how to input the data. So we make sure that this is easily or accessible and can be easily done by others by testing this internally. And once this is fully proof, let's put it that way, then that's what we're going to be putting out there. Huh?
Yeah.
So then any user can just upload this data. They will see, as if you were to use any other tool, any other software tool that, for instance, if you were to use whatever, Aspen, for instance, and then you need to input their parameters for your material, that's what you will see. What are the parameters that you need to input? And then we'll have a way in the system. This is what we are testing internally at the moment, of how then we fill up those gaps in a way that the system reacts fast enough and we can carry out simulations.
And there's organizational stuff as well around, I've spoken to colleagues at PSDI around single sign-on. So having a reliable way of managing new users, because it's a sign-on system, that can be done through a PSDI managed sort of interface and a single sign-on. So that's the sort of thing we'd like to kind of work towards, so that it's something that we can manage going forward, because we don't have the capabilities to have a customer service desk and that sort of stuff.
Yeah. So if you have a UK-based academic email address, then
so there's a very robust, really good system run from PSDI that can manage overseas as well. I think, but it's got a good, well-used sort of automated vetting service as well. So for us uploading data, we can drag and drop, and we can take legacy files in and click buttons to upload and so on, and check things. But the proper way of ingesting data into the system, beyond this legacy information, is through code. So it's single line functions where you take a data frame, send it off, and the API sends it off to our system. So that's the sort of premise of trying to work towards this integration method, which is widely used, but setting up the infrastructure is the big task. So we run this API service, which allows people to take information and also to put information, but we're managing those two directions for different endpoints. So we can choose which information is made public and which tables people can put information into. And just now that's our internal group, but it's obviously a big thing that we're working towards, taking that to a much wider scope. In the coming year.
You have a timeline for when this will be available on the PSDI platform, so the audiences can access it through PSDI?
Yes, so in May,
Perfect.
there's the current cycle with Aileen was a little bit too tight, so we're going to catch the next one and listen out for that. Yeah. Thanks.
Thank you. Thank you, Peter and Susana. Let's open the floor for questions. The first question is for James. Active learning is typically framed in terms of an exploitation trade-off. In your case, the sampling strategy focuses on regions of the phase space where the uncertainty in the potential energy is highest. Does this imply that the methodology is effectively driven by pure exploration?
So a good question. Thank you, whoever has sent that in. So we do still have a mixture between exploration and exploitation in this. So if you think about this equation here, by setting the strength of the bias here, the tau parameter, we can control how much exploration versus exploitation we have. We can make exploration more likely than standard MD by increasing the strength of the bias, or we can weaken it, and then we're doing more of an exploitation where we would be following the regular MD. What we do in practice is set this to keep the forces between the two components roughly on the right order of magnitude to make the biasing typically, say, 10% of the forces that we're getting from the regular model. This is also a bit constrained by the thermodynamic stability. So we need to make sure we don't push it too hard away from where it's stable, but essentially it's a faster way of getting coverage in a constrained sample space. So yeah, good question. Thank you.
So for Susana and Peter, we have a question. How do you see MOFevaluator being used by companies developing carbon capture processes as an early stage screening tool, a process optimization tool, or a decision support tool for technology selection?
Yeah, really the idea here is that, well, companies or anybody that is interested in understanding what's the potential of a material or a technology for their specific case study, get a quick and fast overview of whether that's something that they would like to continue with and invest in. So yes, indeed, it fulfills a series of purposes depending on the questions that you might have, all the way from, if you are an experimental group, for instance, and you have developed a material. Also, just we didn't mention it, but I think it's important to highlight as well that we developed the platform based on meta-organic frameworks, but actually the way we can input data into the tool can be either, there are multiple ways of doing it, and one of them is by just feeding in experimental data. What that means is that you can actually assess any material, as long as any solvent material, as long as you have the data that we need to fit into the workflow. So it's really, as I was saying, it really fulfills different purposes. If you are an experimentalist, for instance, and you have a material that obviously you cannot test for everything, right? But you are interested in the potential of that material for any of the case studies that we might have run, then you can very quickly just, fit in your data then and get an answer for that. Equally, if you are interested in understanding whether a sorption-based type of technology has any potential for a given case study, you can also do that analysis and then inform your decisions. The way we've built it in is to actually provide many different answers depending on the many different questions that you might have. And that's why we have also embedded all those 4 different layers that you saw. Because if you are more in the materials space, you might have more questions, or your questions might be more centered about the specifics of the material. But if you are an engineer, for instance, you might be interested in knowing, okay, what type of process is optimal here with these materials for my specific CO2 source or sink. Obviously, techno-economics also very important from an investment point of view. Can we compete at the moment where it's currently out there? And also ultimately the LCA layer, the life cycle assessment, is key in the sense that you want to make sure that when you implement one of these technologies, you are actually capturing CO2 and you are not emitting more into the atmosphere by all your life cycle, right? So indeed, yes, that's a bit the idea of the tool.
Thank you. We have one more question for the MOF team, MOFevaluator team. Does MOFevaluator only rank materials based on adsorption performance, or does it also include process level indicators such as regeneration energy, productivity, purity, recovery, cost, and life cycle impact?
Yes, sorry, obviously we don't have that much time, so we don't go into the details, but I would refer the person to the paper that I highlighted on the slide. But indeed, we do consider all of that. So basically what we do is like we have the materials, but we put those materials into a process design. So then we've got KPIs or key performance indicators that we obtain at the materials level, but then we've got KPIs that are derived from the analysis in the process layer and all those things in terms of productivity, energy demand, etc. And then we scale up from one column to the number of columns and trends that are required to meet our basis of design. What that means for the engineers in the audience, they will understand this in the sense that basically we are meeting here, we are satisfying a design criteria or a basis of design. So then we need to kind of size our system to be able to fulfill that. So for instance, in the case studies where we have CO2, we've got a point source as the source of the CO2. Our basis of design is basically to make sure that we treat all the flue gas that is coming from your host plant. In the case, so then we size our system in order to fulfill that criteria. So we come up with how many reactors we need in order to have a continuous operation, etc. And then we carry out our techno-economic analysis and our life cycle analysis. It's also important maybe to clarify that also the life cycle analysis considers not only the use phase, so not only the specifics of the carbon capture plant in this case, but also the material synthesis and the materials disposal phase. So basically the whole life cycle system. So all of that is incorporated in the analysis. So then the user, what it gets is a combination of over 50 different key performance indicators for each case study with all that information. So then you can look, we didn't show any specific figure today, but you can actually select in the tool and what Peter has built, what is the KPI that you want to look at or the KPIs, and then you can build up your graphs and your visuals to understand, okay, how good is this in terms of energy demand, in terms of CapEx, in terms of OpEx, in terms of climate change, etc.
Perfect. I have another question. If a user uploads a new MOF crystal structure, what level of information does the platform need before it can evaluate it? And what assumptions does the model make if some data are missing?
Basically, the input data that we required are basic single component absorption data. And then also physical characteristics like, density, heat capacity. Because we've done this exercise of kind of feeding in experimental data in the platform, we know very well that many times you don't have all the data that you need, right? So then if that's the case, sometimes we can estimate it through our simulation engine at the molecular level. And some of the times, if that's not possible, then we take estimates based on informed values from literature and from analogous systems. So indeed, we fill in the gaps if we don't have all the information with reasonable assumptions that then you can obviously test when you look at the results and then understand, okay, if I change this parameter because I wasn't too certain on its value, what would be the influence on our KPIs? So yeah, we fill in the gaps if we don't have all the data, and we've got several ways of doing that.
As I mentioned earlier, all the resources are live now. So this is our PSDI homepage. We have all the resources and tools which will help you support your research. So please do take a look. We also have some upcoming webinars and workshops planned. So we have everything listed on our events page. We also have a workshop coming on the 16th July. It's an in-person interactive workshop from PSDI and the Alchemy AI in Chemistry Hub, exploring what it really means for physical sciences data to be AI ready. This includes experts talks, lightning presentations, and hands-on discussion. It will bring together researchers, data professionals, and infrastructure developers to share their experiences and challenges, practical approaches, and emerging best practices in preparing data effectively for AI and machine learning. Currently, it's available on our events page for registration, so please do take a look. Later this year, we are also planning to launch a PSDI Champions program. So it's like a small flexible funding to support members of community to promote various tools available on PSDI. It's not currently announced, but keep an eye out on our website, and you can also subscribe to our mailing list so that once it is out, you will be notified. All our previous webinars are available on our YouTube channel. So please do take a look. That brings us to the end of today's webinar session. I would like to thank you all the three speakers for giving us a very informative and wonderful talk. Wishing you a great rest of the day and hope to see you soon in the next PSDI event. Thank you.